patient with my schedule mix-up. Let's see. Try to share my screen here. Okay, is that good, the shared screen? I hope.
Yes, we can see.
Okay.
Yeah.
Cool. Yeah. Yeah. So we're going to move from New Zealand to a different set of high mountains. And yeah, as Shamay said, I'm going to be presenting some data that we collected from the Chamoli event last year, which happened in Uttarakhand, India. And we're going to look at what this can tell us about possibilities of early warning for these types of events. And so hopefully I can, yeah, okay. And so we know, and especially here we know because we're talking about it for these several days, that yeah, in high mountain environments, they're subject to some extreme and unexpected events. And here I'm going to be talking mostly about flow events. And so this could be glacial lake outburst floods. It could be complex hazard chains. It could be events like we saw in Chamoli and also in the Seti River in Nepal in 2012 that are triggered by kind of ice rock avalanches. But these are all events that occur unexpectedly. They're unexpected in space and time. They travel up to pretty long distances along river corridors, and they can be extremely destructive. And yeah, because these kinds of, I call them catastrophic flow events, can be triggered by a range of processes. So it can be landslide dams, can be glacial lakes, can be rock falls. This makes them really hard to anticipate in space and time. We don't necessarily know all the sources for these types of events, and it's really hard to predict when they're going to happen because they're not necessarily triggered by, say, rainfall. And so if we can't anticipate events ahead of time, one of the really kind of important things to have in place to mitigate the damage and particularly the fatalities from these types of events is early warning. And so here I'm talking about early warning, not as forecasting, but as really detecting an event as soon as possible and sending out a warning to communities in its path. And so this is, of course, of great interest to many communities in the region, and particularly in the Himalaya. And there are a number of warning schemes in place. And the key kind of commonality with the types of warning that exist today is that they rely on what I call in situ monitoring, right? So you put an instrument next to a glacial lake or a landslide dam lake, or you put an instrument looking at a particular river. And when that instrument detects something happening at its location, it can then send out a warning to downstream communities. And so this is pretty simple. I mean, not simple in practice, but simple in concept, and can work really well, right? If a lake level sensor sees the lake level dropping, then we can know probably we should warn communities downstream. However, the problem with these types of methods, or the limitation, is that they are location specific, right? So if you're not monitoring a particular lake, you won't be able to issue a warning for an event that comes from that lake. And if you're not monitoring a particular river, you won't be able to issue a warning for that river. And this is a particular problem in the Himalaya where there's a lot of glaciers, there's a lot of tributaries, there's just a lot of ground to cover, a lot of potential source areas, and it's just not possible to install monitoring equipment on all of them. And then you add in that there's a problem with transboundary rivers, so many events flow from one country to another. And we can see that while this in situ monitoring can work well, it just can't cover everything. And so what we're really interested in is, can we come up with a method to detect events remotely, right, without needing local equipment? And I'm going to argue that we can. And so the technique that we are looking at for this is seismology. And this is because we all know that earthquakes generate seismic waves, but so do all sorts of other events. So basically, any process that transmits energy to the Earth's surface will generate a seismic signal that we can measure with standard seismometers. And so this includes, of course, things like landslides, rock falls, debris flows, and even sediment transport in rivers. And so the question is, can this be used to remotely detect flow events? And so we started looking at this really motivated by an event that we observed in Nepal in 2016. And this was a glacial lake outburst flood from a pretty small lake, actually. It wasn't a terribly large flood. And it passed through a seismic array that we had along the river. And we could see very, very clearly the flood passing through the instruments that we had close to the river. But we could also see this flood on instruments that were quite far away. And so here on these plots, and these plots are showing time on the x-axis, frequency on the y-axis, and then the colors are the amount of seismic power in a given frequency range at a given time. So this is kind of just giving an overview of the seismic signal in frequency, time, space. And so where red means higher power, and that basically tells you that something's happening at that time in that frequency range. And so what we can see here is that first at a station that was 25 kilometers from the source of this flood, we see a very nice flood signal. This was not a big surprise. But what we also see is in a station that was 60 kilometers, so well downstream of this event, we see a very clear signal of this outburst flood. And we can see the seismic energy from this event from when it initiated. Right? So we can actually see the full sequence of this event from 60 kilometers away. So that's kind of exciting. If suggests if we can systematically observe these events from a distance, we could maybe detect them as soon as shortly after their initiation. Yeah, so, but that's not a lot of data to work on to actually figure out what is the feasibility of this type of monitoring. And so I did a search through kind of all publicly available seismic data I could find to see what other events may have been captured seismically, and it's not very many. And so here are two examples that I was able to find. So one from Bhutan in 1994. And then this one, actually, you might be hearing about tomorrow, I suspect, from Martin Geertsma. This was an event that happened in British Columbia in 2020. But most of these were only captured on maybe one or two stations, and it's still not much to go on. And this is where the Chamoli event comes in. And I'm sure most, or all of you have heard about this event, which hit in Uttarakhand, India, February 7th last year. This was quite a destructive event with a large number of fatalities. So unfortunately, it hit a hydropower plant that was under construction at the time. And it's also the most well documented in videos and photographs of any of these large floods I've ever seen. And so, yeah, just a really quick overview of this event. And so here's a satellite image actually taken while the event was happening. You can see the dust clouds here. And so this event originated down here as a ice and rock fall avalanche. This mobilized material in the valley floor traveled down this tributary took a turn into the Rishiganga and then into the Dalinganga River and flowed out downstream. And so just to zoom in on the source area, again, this was a very large rock slide with some amount of ice, about 25 million cubic meters. It fell about 2,000 meters onto pre-existing valley floor avalanche deposits, and kind of this whole mass of sediment, ice, debris, and eventually melted ice and snow started to travel downstream. And so for us, the exciting part of this event is that it occurred within a dense seismic network. And so this is a network that is operated by my colleagues and collaborators at the National Geophysical Research Institute in India. And it's here to monitor earthquakes, as most seismic networks are. What we can see here's the rock slide location, so the event initiation. And then there are 76 broadband seismometers kind of arrayed around this event. And so this is a really unique opportunity to see what actually can we detect seismically, at what distances can we locate things. This is a really nice opportunity to test the feasibility of seismic early warning of these events. And so, yeah, this is just another look at kind of the flow path here. There was one station quite close to the river, which very clearly shows the flood passing by and the kind of near field seismic signal of the event. But we can actually see this event broadly across the network. And here again, this is the station that was near the river. We can see this red splotch here is when the flow is actually passing very close to the station. You can see the effect of the moving seismic source. We get a better overview if we look at the farther off stations that aren't affected by this changing distances. And here we can see actually some of the dynamics of the event. And so we can see in this data, actually three really distinct phases of the event. So first we see the rock slide very clearly. This is this labeled 1 here, a really high amount of energy up to quite high frequencies, but really concentrated at low frequencies. And then we see this what we call phase 2, which has a lot of low frequency energy. You can see it quite clearly here. And this transitions actually into quite a different seismic signal in what we call phase 3, which really looks more like a debris flow concentrated flood. And so we can look at what are the detection limits of these different event phases. And yeah, the first one, the rock slide, this was very energetic. You can actually see this up to at least 1,000 kilometers away, stations in Pakistan, in Nepal, in Afghanistan. Very easy to detect, that's no problem. The phase 2, which we interpret as kind of this mass flow, basically, so without much water involved yet, or yeah, relatively low amounts of water. This is also quite detectable. It's very energetic. We can see this really across the entire network. And here on this plot on the top, we're looking at distance from the source, the amount of seismic power in a pretty limited frequency range. The event here is in these dots. And then for comparison, I'm showing the kind of average background seismic noise at each of these stations. And then the bottom plot, this is a kind of basically the same information, but in map view, this is just the signal to noise ratio at each of the stations, moving away from the event source of the star. But what we're really interested in, if we want to think about flood warning, is the phase 3. So we think this most closely resembles what we'd expect to see in, say, a glacial lake outburst flood. And here, this is much less energetic. It can still be detected at pretty long distances, depending on the characteristics of the station. So station at about 100 kilometers, we can still see the signal from this event, but it becomes much more patchy if we look at the signal to noise ratio. Yeah, and so it's useful to be able to know that an event is happening, but if we want to be able to issue a warning, we have to know where it is. And so we also tried out two different methods of locating this event and seeing if we could actually track its movement downstream. And these two maps are illustrating that, in fact, we can. And so these are calculated with completely independent information. On this panel A, this is using just the amplitude of the seismic signal with no frequency information. In panel B, this is using cross correlation of signals, so basically just the frequency information with no amplitude information. And so it's actually kind of amazing that they really correspond pretty well, not 100%, but pretty well. And both of them are pretty effective in being able to both locate the event and actually track its movement downstream. And so on the amplitude-based method, it actually gets really confused by the signal from the station here as the flow is traveling around this bend. So it's not so effective after the first 20 minutes or so. But we can actually track the event using these cross correlations, for over an hour, really to the point where it's not that big a flow anymore. So where it's starting to kind of decay enough that it's not a catastrophic event anymore. And so this is really encouraging. And we can validate this information by comparing it to some external sources. And so we can identify the position of the flow using satellite imagery, using some gauges. Here we're showing these points in blue. And yeah, it matches our estimated seismic locations pretty well, actually. And so on this lower plot, this is a plot of just velocity with distance, comparing information from all these different sources, including estimates of flow velocity from observer imagery and video. And so this is very encouraging. We can actually detect downslope, downstream movement within a few minutes of the initiation of this event. However, there are some caveats here, and this is that for the flood part of this event, the detectability or the detection limits really depend on the stations. And the reason for this is background noise. And so all of these stations were installed in towns and villages. This event happened in the daytime. And there's a lot going on in these areas in the daytime. And the frequencies that are generated by an event like this overlap with the seismic noise that is generated by people moving about, driving their cars, turning on equipment, and all this full array of anthropogenic noise. So you can see this really clearly. This is a full day from this station AUL, which was very close to the river. Here is our event. And yeah, it stands out from the background, but imagine if this had happened at night when it's significantly quieter. And in fact, the nighttime background noise in these averaged across all our stations is about 9 decibels lower than the daytime noise, which is significantly lower. So you can see in these difference between these red and blue diamonds. And so this is a problem, right? We want to be able to detect events during the daytime as well as during the nighttime. And this suggests that yeah, station location needs to be considered a bit more carefully if we want to be able to deploy a network like this for early warning. And yeah, but it's not just anthropogenic noise. The other main issue in this part of the world is actually noise from other geomorphic processes, and particularly rivers. So rivers generate a lot of seismic noise. For stations close to the river, they can be completely dominated by river noise during the monsoon. And so we see for a subset of our stations the average background power increases by up to 13 decibels during the monsoon as compared to the dry season. And so this is also a big problem, suggesting that, if most of these events will occur during the monsoon, and so this is when we want our best ability to detect them, not our worst. So yeah, some guidelines for how we think about constructing our seismic networks for this purpose, far away from rivers as possible and as far away from people as possible. But with these caveats, this suggests that yeah, this is possible. Theoretically, if we had our algorithms all figured out, if we had everything set up, and we'll be clear that we don't, this was all manual, we could have detected this event within a few minutes. And this would not have given a huge amount of warning time for the region because the distance between the source and the most damaged areas was not very far, but maybe up to a few minutes, maybe even 10 minutes for the Tapovan hydropower plant where most of the fatalities occurred, and up to 30 minutes for the first kind of major city on the flow path. And of course, there's a ton of work to get to making actually an operational system. This is something that we're planning to be working on over the next years. One of the first needs actually is just more data from more events. One of the big problems, particularly in the Himalayas, that a lot of the seismic data is not open, or most of the seismic data is not open and can be quite difficult to obtain, but this is also where all the events occur. So if anyone would like to cooperate, has access to some seismic records of any kind of large flood, outburst flood, glacial lake outburst flood, please get in touch. Yeah, and that is the end.
Okay. Thank you, Christian, for the very interesting talk about the Chamoli event and other events you have been captured the seismic signals. Are there any questions from our participants? Oh, no, that's Jim was asking Saskia for some geophysics measurements. Yeah, probably Saskia can answer during the discussion session. Yeah. Kristen, I actually have a few small questions. Actually, after seeing your paper on Science, it's actually giving people really, kind of a promising method to getting this early warning and some early recognition of the some far field headers which people can not really reach to the site. Like you can use the seismic station data to reconstruct and to do the early warning. My question is similar like the Chamoli event, like minimum how many stations you need to have in order to getting this early warning signal?
Yeah, so that is the good question. So yeah, there's a trade-off between event size and how far away you can detect it, right? So the bigger the event, the farther away stations can see it, and the fewer stations you will need. So the station spacing in Chamoli was about 20 kilometers. This was more than enough, clearly, for this event. In the end, we only used, I think, 10 stations to do most of our calculations. Yeah, so in terms of thinking about a design of an early warning network, the first question needs to be well, how much money do you have? That's the first question. But what do you want to detect? What are your limits? What are you, do you say, okay, I need to find every large debris flow? Or do you say, well, okay, only the really largest glacial lake outburst floods or Chamoli type events? And so, Yeah, I mean, the answer can be anything. It just depends on what you want.
I see. It depends on the magnitude of the event and how much information you want to know. And
Yeah.
I have another question, but probably I can ask later because Ashim is asking a question.
Yeah.
I see he has living. Yeah.
Hi, Kristen. Thank you. That was a wonderful talk. My question to you is about detection of some precursors. For example, in the Chamoli event, we had some cracks that started forming before the event. And all these precursory signatures are very important in terms of early warnings. And in the same valley, we could see some activity during 2016, where how do you think that seismic signals can give a warning well ahead in time before the actual event?
Yeah, so it's possible for sure. Again, this kind of comes to the size spacing question. So yeah, you can absolutely detect cracking and precursory activity seismically. Whether you can detect it at distances of tens of kilometers depends exactly on the processes happening. So if you have kind of like stick slip motion of a large mass, you should be able to potentially detect that quite far. If you have kind of really small scale cracking, you actually can see that seismically with very close stations. Yeah, and then the avalanche, yeah, again at the closest station, probably that would be in the record. Unfortunately, as I said, data access is always a problem, and even in a good collaboration, we actually have not seen precursory seismic data. Like we just don't have access to the data. Similarly with data from 2016. But yeah, definitely if for very detailed monitoring of a small area, so if you identified a slope as moving slightly or being potentially unstable, if you installed a couple stations in the near field, yeah, you really should be able to track very closely what is happening.
Thanks, Kristen.
Okay, thanks, Christian. Maybe, yeah, I have a few other questions. Maybe we can discuss a little bit for the discussion session later on after all the presentations.
Yep, sure. Thanks.
Thanks. Actually, now it's my turn to give the talk on some of the similar events in the Tibetan Plateau. I'm going to share my screen now.